Okay, so let's look at how k-means is greedy alternating minimization of the cost function we had written down. Let me write it down again. It's the sum over the data points, or you can make it the average by dividing by n of the average distortion, which is the probability that you're assigned to the kth cluster and the Euclidean distance squared between the data point I and the cluster center for the kth cluster, and we want to minimize over the assignment probabilities and the MKs. So let's say we you're given the cluster centers. So you start with so initialize with some choice of MK of these cluster centers, MK, right? Equals 1 to capital K. So basically what we do then is assign the data points to the cluster center. So if I look at the ith data point and say, okay, let me change in color. This guy, the assignment probabilities have to sum to 1. Your contribution to the cost function is assignment probability times xi minus mk squared, and you basically have a sum weight of 1, and all these are non-negative quantities. What would you assign it to be? Where would you assign it? Well, you would assign all your weight to the smallest possible contribution, right? So immediately you know that this has to be essentially a deterministic assignment. The way I've set it up, it is basically 1 for k, the k that minimizes this, right? So arg min over j, x minus mj squared, and it's 0 for all other k, right? So basically I assign, so xi is assigned to the ck, where k is arg min over j xi minus mj. So the assignment step is go to the closest cluster center. So that's our assignment step. So now that we know we will go to exactly one cluster, we can write down the cost function more simply. Basically, let me change pen color. The cost function becomes delta squared is sum over I in ck xi minus mk squared, and of course summed over the clusters, right? So basically you're saying for each cluster, what is the distortion I have for the points that have been assigned to me, and then of course I have to sum over clusters. And this is a quadratic in MK, and when I'm optimizing over MK, what is the relevant part? I in ck xi minus mk squared. Let me change pen color. This is the contribution to the cost function due to the kth cluster center. So this is what I have to optimize. The contributions are additive, and so I can just optimize them separately over MK. And just to take the derivative of this with respect to MK, that becomes easy because look at this guy. This is just xi minus mk transpose xi minus mk, and when I take the gradient of this, with respect to mk, I basically get, when I differentiate with respect to the first mk, I'll get minus xi minus mk, and when I differentiate with respect to the second mk, I also get the same thing, so I get minus 2 times that is the gradient of the ith term there, and I sum over I in ck, and this gradient has to be equal to 0. So the minus 2 can be taken out, and so basically I have summation I in ck xi minus summation I in ck mk equal to 0, which is basically saying that I'm just adding up mk ck times, so that this answer for this is straightforward. So mk times the number of points in ck is equal to summation I in ck xi, and so mk is 1 over ck summation I in ck xi. So basically this is just the centroid of that cluster. So this can be, this is the what have we done? We basically first assigned the points to the nearest center, and then we recomputed the center to be the centroid of the points that have been assigned to it, and we just alternate those 2 steps. And it's a greedy procedure. Each step of the greedy procedure can only decrease, you cannot increase the cost function. So this procedure is guaranteed to converge. Of course, what it's guaranteed to converge to is not necessarily the global minimum. But this is guaranteed to converge to a local minimum. So guaranteed to converge, but to a local minimum. So in practice, how do we deal with that? Well, the local minimum depends on where we started from. So there's 2 options really. Many options, but so this depends on the initial condition. So we'll often initialize randomly by choosing k points in random from the training data points that have been given to us from the data points we wish to cluster, and then basically do it, get some delta squared at the end, and then take another random initialization, and basically do several random initializations and choose the one that gives me the best distortion. So that's one possibility. So several random initializations, and then choose the one giving the best distortion. That's one possibility, and it's pretty simple and works pretty well. The other one, which has some theoretical guarantees, is a so-called k-means ++ algorithm, where the initialization is subsequential, and the way that works is choose first point at random. So basically M1 from the training data randomly, and basically, but from that point on, so assume you have chosen, let me just define it recursively, chosen M1 through mj. Remember, this is just for the initialization that I'm talking about. And now I need to take one more point. Compute delta I as the minimum distance that I have for any given point, a minimum over j of xi minus mj. Let me make it squared here. Delta I squared is that, and then choose the points that are furthest away. Still keep it random, but try to choose the points that are sort of far away from the current centers. So choose mj plus equals xi with probability proportional to delta I squared. So you tend to choose points that are far away from the current center. So you're spacing them out, but still keeping some randomness so you don't get locked into some weird deterministic setting. So that's sort of the idea behind k-means plus plus. Of course, the probabilities have to sum up to 1. So the probability of choosing this guy is going to be delta I squared by summation over, I don't know, L of delta L squared. And of course, you wouldn't choose any of the points that you already have because the delta i's for those guys will be 0. So that's the k-means plus plus initialization. It has some nice properties. I would urge you to look at the references in the handout. There are some properties under certain circumstances. The delta squared you get from them is guaranteed to be within some factor of the optimal delta squared. So that's it's great, but of course it costs more in the sense that you need to go sequentially to choose these centers, and so it's not particularly well suited, for example, for very, very large data sets and very large values of k necessarily. You might go with these random things. It may not be very well suited to streaming implementations, but it's such an interesting initialization that there's been a lot of work trying to parallelize these things and trying to improve it. So it's an interesting literature that we might be interested in looking at. Okay, so let me summarize the k-means algorithm. You start with some initialization, and then you have an assignment step where you assign points to the closest cluster center. So the clusters you form, ck, is all the training data points such that which are sort of the closest to the cluster center corresponding to that, right? So xi minus mj squared, you looked at that, and you minimize over all the cluster centers. That's the assignment step, and the update step is just compute the centroids, right? So mk is 1 over ck summation I ck xi, right? So this is a centroid computation. Couldn't be simpler, which is why the k-means algorithm is one of the most popular, the most popular approach for clustering. We will hint at when it doesn't work. It's when we link it to Gaussian mixture models, we'll see that effectively k-means is trying to can be thought of as a limit of Gaussian mixture modeling, but where the covariance is always spherical. So weird shapes, clusters with weird shapes, are harder for k-means to capture. But of course, there are ways around it too. There are kernel methods around it. But this is sort of a workhorse, and there have been huge numbers of papers on various aspects of it, speeding it up, modifying it to deal with as we go to higher dimensions. We may wish to normalize the data and have spherical k-means, so-called spherical k-means. We might want to have online versions of it which sort of update as data streams in. So there's huge amounts of variations, and I would urge you to explore the literature if you're interested.